Hi everyone, and welcome to this HPC Knowledge Portal meeting presentation about Elbencho. My name is Sven, and I'm the creator of Elbencho, a new storage benchmark for HPC, AI, and of course, lots of other things. So why did I create Elbencho? Well, on the one hand, because it's part of my daily job to help people get the most out of their storage systems. And of course, back in the old spinning disk days, that mostly came down to simple streaming, read and write benchmarks, because you could not do much other things with those spinning rusts. But nowadays, with flash drives being more and more available to everyone, there is, of course, a whole new range of access patterns that's much more interesting and needs to be qualified to see what the applications can get out of this. And so, of course, I've been working with all the usual suspects among the storage benchmark tools, like MD-test, for instance, for metadata or lots of small files, or IOR, mostly for large files, or things like FIO, mostly for block devices. And on the one hand, while there were things that I liked about each of these, right? For instance, FIO, I very much appreciated the live statistics view. On the other hand, there were also things that I did not like so much about them. And one of them was, of course, the specialization of these tools, right? It was always hard to explain to the customers why they need one tool for one use case and then another tool for another use case. And for instance, while, of course, you expect a modern storage benchmark tool to be able to also test distributed storage, some people were not even familiar with MPI, right? Or there were cases where it was hard to do an MPI install in the first place. For instance, if you wanted to test performance directly on the storage service. So these are all things that I wanted to fix with Elbencho, right? Have that one tool that works for all of these use cases. And of course, since we're also in the AI era, being able to benchmark storage throughput directly to the GPUs is, of course, also a whole new interesting thing that was not covered by the traditional benchmarks so far. And luckily, when I created and published the first version of Elbencho about almost exactly 1 year ago, it quickly became adopted by a number of people around the globe. And there are also several contributions nowadays from many people, which I, of course, appreciate a lot. And also, of course, a lot of helpful comments and suggestions from all kinds of people. So feedback is definitely welcome, of course. And where do you get Elbencho? Of course, as all good open source software these days, it's available on GitHub. And what can you actually measure with Elbencho? Well, hopefully all the interesting metrics that there are for modern storage systems, right? But I thought, while I have some of these examples here on the slides, it's of course much more interesting to actually go through them in a live demo, right? And what's the first part, of course, of a live demo? Well, how do you even get Elbencho? So let's start with that. So let's bring up a browser window and search for Elbencho. There we go. Okay, and there are basically two ways to get Elbencho. One is you can build it from source, or if for some reason you're not able to install the dependencies or do not want to go through the build process, then you can also get it directly from Docker. So let's start with this one. As a very first simple step, here you have your example that will only show the help, but that's all we need for this demo. Here we have some VM. And that's it. There you have Elbencho and are ready to go. However, I would typically recommend to build it rather from source, because if you build from source, then you can also compile in GPU support, which is not automatically available in the Docker container. And you also have the tab completion installed on the host system. So let's see how that works. Back to GitHub. Here we have the dependencies that need to be installed. This is Ubuntu VM, which I'm using here for this demo. So let's copy this dependencies command. Nothing to do because I already installed the dependencies. And then we continue here, clone the GitHub repository. That was quick. CD into the directory. And then we're already ready to build. This should only take about 20 seconds. One thing you can see here right at the top is that the system, or the makefile more specifically, already discovered that I have the CUDA libraries installed and also the GPU direct storage libraries installed, so it automatically compiles Elbencho with support for GPUs. If that would not work for some reason, then you can use make help. And see here that you also can specifically request to enable CUDA and GDS support, like this, for instance. And then if you believe it should be enabled, but did not get enabled by default, right, then you would see the error message here for why it did not get enabled. But this time it did. So here in the bin subdirectory, we have the binary available. If we use the version command, we'll also see that it includes these optional features, CUDA and GDS support. But better than just having the binary somewhere lying around would, of course, be to build a package so that we have the auto-completion support. So let's say make deb, because this is a Debian package-based system. Otherwise, I would use make RPM. There we have our Debian package, and then we just do apt install sudo, of course. And okay, in this case, it was already installed. Otherwise, it would be now. Now it's possible that you might need to exit the shell and reopen it again just to enable the tab completion, which I already did in this case. And now I can use -- and hit the tab key twice and see that it automatically would complete all the parameters that are available, for instance. So that's it, and we're good to go. Okay, so what's the first thing we want to test? How about random IOPS? And by the way, we'll also include hints about single and multiple client testing and generating result graphs. So back to our VM. Okay, let's bring up the Elbencho help. As you can see here, there are sub-help commands for specific use cases. In this case, where we want to test random IOPS, we would usually already have a block device on which we want to test this, or we would be working with large files inside which we then can test these random IOPS. So let's bring up the help for that. And as you'll see there, it contains different examples as an easy starting point, right? So in our case, let's start by first creating a large file in which we can afterwards test the random read IOPS. Here I have a Samba mount to my very slow NAS system right to my desktop here, so we won't get any great numbers, but that doesn't matter for the purpose of this presentation. So this is the file name we want to create, -w to write a new file. We use a single thread because this NAS system is using a spinning disk, right? So many threads wouldn't help a lot. Block size in this case is 1 megabyte. We want to create a 2 gigabyte file, and we use -- direct to bypass the caching of the file system and make the data go directly to the drives. If we wanted to here, we could also use multiple files, of course, like In this case, for instance, right, we just provide a second file name or the path to a second block device, or we can also use bash magic like this to create 128 different file names, but for the purpose of this demonstration, a single file will be good enough. And another parameter that I included in the end here is the block variance. This is only required for storage systems that, for instance, do compression on the files, right? In that case, you don't want to only write zeros to the files, because then you certainly wouldn't benchmark what you actually want to benchmark. Instead, you want to write randomized data. That, of course, comes at slightly higher CPU usage, but otherwise it's not really noticeable. So usually not a problem, but it's not enabled by default, right? So in this case, we'll use it just to create that 2 GB file. Should not take too long. Okay, there we go. And one thing we can easily tell from the result of 375 megabytes per second here is that my NAS box certainly did not fully disable the caching, or the drive did some caching by itself, because this is certainly faster than my single spinning disk can actually do. But doesn't matter for this presentation. Another thing that we can do easily, of course, is to use multiple hosts for the same test case, right? So how would that work? For that, we would just start Elbencho in the -- service mode. Then it runs on that particular host. Here we're running on Devil 1, and we'll start service instance on host Devil 2. And then it will just sit there in the background and wait for commands from a master instance. So I'll start a second service instance on this very same host on Devil 1 now. Okay, both are just running in the background and doing nothing so far. So how do we actually use them? All commands that you see in this presentation, you can easily use with multiple hosts just by adding the parameter -- hosts and then comma-separated list of host names, like Devil 1 and Devil 2 it would be in this case, or also by specifying a host file, which might be easier if you have multiple hosts. So let's see how that would work. For that, we would just echo the host names into a file like this, for instance, into my hosts here now. Then go back and say host file, my hosts. And maybe remove the comment character. And I should have used tab completion like this. And now here we go. And as we can see now, Elbencho is showing the live statistics for each of these two hosts, which actually run on the same physical host, right? So it's not a great result still. Here we see the elapsed time and that 2 hosts are still active. Okay, and now we're done. One thing that you can see here that you typically have not in other benchmarks is that we have 2 result columns. So one is labeled first done and the other one is labeled last done, both associated with a timestamp. And in this case, we had 2 hosts, each having to do half of the work, right? We created a single 2 GB file. So each of the hosts had to write 1 GB of this file, and it's in the nature of things of a distributed system that one of all the hosts that we have finishes first and one finishes last, right? So usually what a benchmark tool is showing you is only the last done result, so the point in time when the last host or the last thread finished its work, and then the average throughput until then. And the extra thing that Elbencho is showing you is also the point in time when the first one finishes. So we see here, for instance, for fairness, where this is relevant, right, that they finished closely together, which is a good thing, right? There's not a big time difference between them. And usually if this would have been a bigger run and a bigger delay between the first and the last finisher, then we would also see that typically the average throughput for the first finisher is higher, because at this point in time, you still have all the threads active, and then usually there comes the tail of less and less hosts or less and less threads being active, so the throughput goes further down, right? And I found it interesting to see the difference between these two results. Okay, and for the rest of the presentation, we'll not be using the distributed mode, but you know now that it exists and that it can be used in every case. So we're basically done now with the service instances, and we can shut them down. How does that work? Again, by providing the hosts file. What was the name? My hosts, and using the quit command. That now just stopped all the service instances that we had running. So if I would try the same thing again now with my hosts file, then it would fail, of course, because they have been stopped as intended. But what we actually wanted to do is, of course, random read IOPS testing. So let's bring up a command to do that. What do we have here? We have, again, our large file that we just created for this purpose. We use -r to do reads. We use, again, only a single thread here. Could, of course, be any number of threads if we wanted to. A block size of only 4K. We use, again, direct to bypass caching as much as possible. --rand to do random I/O inside this large file. And in this case, we're also interested in seeing latency results. And typically, the IOPS do not change a lot over time, right? So if we wait only 10 seconds or 2 hours for random IOs in these files, typically they would be all the same. So in this case, we limit the benchmark duration to only 10 seconds. So let's see what we get. And 10 seconds are over. As expected, less than 1 megabyte per second. In the future, I'll auto-scale this also to kilobytes per second. Then you would see some number here, but the 0 basically means that it's less than 1 megabyte per second. In total, we read only 4 megabytes in these 10 seconds that we waited, and got 123 IOPS out of this drive, with an average of, here it says microseconds, so 8,000 means it's 8 milliseconds in average. Worst case, 19 milliseconds, which all looks pretty normal for a standard spinning disk at least. And since we only had a single thread in this test, there is, of course, no difference between first done and last done, because there is only one thread here. Now, typically when doing this kind of tests, it's not only interesting to see what you get with 4K, but also with other block sizes or other thread counts, for instance, right? So typically you would, for instance, start with multiple block sizes and then try to get a graph out of these results, right? So would be, of course, a bit boring to only look at the console output or show that to a customer. So for that, let's bring up a command line that can test multiple block sizes. What I have here is a simple shell script for loop, right, where block is the variable, and we have multiple values for this variable, starting with 4K, 16K, 64K, and so on, up to 1 megabyte. And from that, in the end, we want to create a graph instead of only looking at the console output. So one option that Elbencho has for that is a CSV file that we can specify here. So all the different results will be appended to the same CSV file. And just to make it more interesting, in this case, we're using 4 threads. Again, we read only. Here we have the block size as our variable from the for loop. We use our large file again. This time we limit to only 5 seconds, which seems way too low for a normal test, but this is only for demo purposes. And of course, we do random IOs again. So let's start this. Now we're iterating over the different block sizes. Okay, and we're done with that. So now let's take a quick look at the generated CSV file just to see what's in there. Results.csv was the name. Larger. Okay, not very human friendly, of course, but it should not be. It should be machine readable. So now we could take this and copy it, for instance, to Google Sheets or Microsoft Excel to afterwards generate a graph from it. But to make that even easier, and because I need to do this a lot, I thought it would be more helpful if Elbencho would just bring a tool that can automatically create these graphs. So the tool for that is called Elbencho chart to generate charts. Let's bring up the help for that. As you can see here, it also includes examples, exactly an example like we used, the for loop to run different block sizes. And then afterwards, based on that, you can automatically create a graph. So one question is, of course, which columns do you have available in that CSV file? You already saw that that's not really human friendly, right? So Elbencho chart also includes an option to show you the columns that you have available in the CSV file like this. And what we see here is, of course, things like the elapsed time or the benchmark parameters that we used, like number of threads, and also the result values like IOPS or megabytes per second done. Similar to the two columns that we're seeing, there's always the first done column and the last done column. So let's use the tool to actually generate a graph. What I'm saying here is that on the x-axis, I want to use the block size, which is the variable that we had in the for loop. On the left-hand y-axis, I want to see the megabytes per second by last finishing thread. And on the right-hand y-axis, I want to see the IOPS. And as expected, the IOPS, of course, go down as the block size increases. And at the same time, the throughput increases also as the block size increases. Okay, so that was working with large files and random IOPS. And probably you already guessed it, what might be the next thing now? Lots of small files. So for lots of small files, of course, we would no longer give Elbencho each individual file name. Instead, we'll give it a directory. So internally in the code, the previous one was called file mode, and this one is now called directory mode. So let's create a directory that we want to use, again, on our NAS box here, and bring up an Elbencho command to test lots of small files. By the way, the order of the parameters really does not matter, right? So the benchmark path here could also be at the end of the parameters, and the order of these parameters also could be different. What do we have here? Our test directory could also be multiple test directories. In that case, Elbencho would evenly spread all the files that we create across the multiple benchmark paths, but here we have only one. We're using 5 threads, and now we need to give Elbencho a number of directories that it should create. The number of directories here is per thread. So this means 10 directories per thread, meaning 50 directories in total for the 5 threads, and the number of files per directory, which is 100 here. So in total, that makes 5 times 10 times 100, so 5,000 files in total now. Each file should be 128 kilobytes in size. And we want to use a block size of 128 kilobytes, so that effectively means each file will be written or read in a single operation. Again, we're using direct to bypass the caching as far as possible. -D because we want to create the directory structure. -W to actually write or create the files. dash R because we want to read the files afterwards, dash stat as a metadata operation to only stat the files afterwards, then dash capital F means we want to delete the files afterwards, and dash capital D to delete the directory structure also afterwards. And in this case, we're also interested in the latency again. So we add dash dash late here. Okay, creating the 50 directories was quick. Now we are writing these 5,000 files from 5 threads, as you can see here. At the top, we have the aggregate throughput for all the threads. Stat phase is also already done. Now we're in the read phase. And we see, as usual for spinning disks, the numbers here are fluctuating quite a bit, depending on how the disk decides to seek or not to seek. Okay, and we're done. And again, usually, of course, you might want to do this again in a loop with different file sizes and then create a graph from it, or also with different thread counts, if you like. Let's take a quick look at the results that we got. One thing we see here from the write phase, for instance, is that we now have 2 latency results. One is the pure I/O latency, so that means only the read or write operation itself, averaging here about 1.3 milliseconds. And the other one we see is the file latency, as it's labeled here. That means it's not only the pure I/O operation, the read and write, but it's also including the close and open of each of the files. And we see that the difference here is quite significant, right? So of course, opening and closing lots of files adds a lot of extra overhead to the tests. And in general, if you wanted to, of course, there would be nothing preventing you from saying that you want to use larger file sizes here. So if I wanted to, I could use 100 gigabyte files here. The difference from the other mode, the file mode, where we specify a file name here directly, is that in the file mode, this would be a shared file where all threads read or write shared from the same single file. And in this directory mode here, it's a file per thread, right? So each thread would create different files. So now it's finally time to also include some GPUs in this benchmark. And for that, we'll switch to the big iron DGX A100 that we have in the lab here. While I'm doing this, the system is also being used by others at the same time. So I'll be light on the number of threads that we use, and we will not draw direct conclusions from the results that we get here, right? Because they might be interfered by others doing stuff with the same storage system. But at least I wanted to show you how this generally works. So similar to how you can always add a -- hosts option to use multiple hosts, you can also add for all of the tests a -- GPU IDs option to copy the data from or to GPU memory. In this case, we have 8 GPUs on the system that we see here on the right-hand side, if that's not too small for your screen. That can be a comma or a space separated list. So here I'm using just the echo command and some bash magic to expand this to the IDs 0 to 7, which matches the CUDA GPU IDs that we see here from 0 to 7. This is an AMD-based system, which also has 8 NUMA zones. So here I'm also binding the threads to these 8 NUMA zones. Otherwise, I'm just reading in file mode now the number of large files that are already pre-created. I use -- CPU to also have the CPU utilization in the end results. We're time limiting this to 20 seconds, -R for the reads, 8 threads, rather large block size here of 4 megabytes. Again, -- direct to bypass the caching. And we want to use GPU direct storage for this. So for GPU direct storage, NVIDIA introduced a new API called QFile. So the parameter for this is called --QFile. And there's an extra option to speed up the transfers by registering the buffers for RDMA. So with GPU direct storage, the network cards can actually do direct RDMA transfers into the GPU memory. That's where all the speed up with GDS comes from. So let's run this and see what happens. Okay, here we go. About 11 gigabytes per second. We see that the NVIDIA SMI tool is reporting that Elbencho is using all these 8 GPUs. And the other interesting thing we see here is that the GPU utilization is 0%. That's because the GPU does not need to do anything. The data is transferred into the GPUs, as I said, directly from the network card. Okay, in comparison to that, Elbencho can also do the classic GPU transfer style, which means it's not using GPU direct storage and instead first reading all the data into host memory, and then afterwards, after each block read into host memory, it's being copied to GPU memory. So the parameters mostly look similar. Again, we're doing our reads with 8 threads for megabytes and so on. We're doing the NUMA binding to all 8 NUMA zones that exist in the system. And we're again specifying all 8 GPUs that we have. But here now we leave out the parameters QFile and GDS buffer registration. Let's see what happens for that. Again, NVIDIA SMI is reporting that we're using all the 8 GPUs, but you see the difference here now. The GPUs have their pipelines active to do the actual memory transfer from host memory into the GPU memory. Okay, in general, the result is a bit lower. That's on the one hand expected, but as I said, the system might also be used by others, so let's not draw direct conclusions from this. And then the third option that we have would be, of course, to do the classic transfer, not using GPUs at all. So here we specify our normal parameters, including the NUMA binding, for instance, which actually means that all the 8 threads that we have here get bound round robin to each of the NUMA zones that we have, right? So each of the threads is only assigned to one of the NUMA zones that we have in the system. And in this case, we leave the GPU parameters simply out. As expected, NVIDIA SMI is not reporting anything here, so nothing is happening to the GPUs. Throughput is fluctuating a bit. Yeah, maybe someone is accessing the storage system. And the result is not all that relevant, I would say, but usually you would expect that GDS gives you the best throughput because it's doing the offloading for all the copying, right? The data is going directly from the network card for reads into the GPU memory. Then the second fastest should be just transferring into host memory. And then the third and last fastest should be the classic GPU transfer because it's equivalent to doing the normal host memory transfer and then afterwards, as an additional step, copying everything over into the GPU memory. Okay, so that's that. And finally, I also wanted to give you a very, very quick look at the source code, at least, in case you're interested in contributing. Let's bring up a browser for that. Here we go. Most of the action is actually happening inside the worker threads, like you would expect. There's a remote worker class that's for coordinating the service instances remotely. And then no matter whether it's running in standalone mode or in remote mode, the actual work is being done in instances of the local worker class. So there's one instance of the local worker class for each thread that you specify. And as you can see inside here, we have the run method that each of the worker threads runs. That's basically an infinite loop, which is after doing the basic initialization, just waiting for commands from the standalone coordinator or from a remote coordinator. And then depending on which benchmark phase it should run, it will enter the corresponding method. So let's assume you're interested in finding out what happens when files are created in directory mode, right? Then we end up here. So let's quickly search for that. Here we go. So now we create our files in directory mode. And as you would expect, there's an outer loop over all the directories that we specified on the command line and an inner loop to iterate over all the files that we have in each of the directories. And if this would be a create file, so a write phase, right, then inside here, we would have the function that ultimately does the actual file creation and file write. And this is a function pointer because it can be mapped depending on whether you specified asynchronous I/O by an IODEPS parameter or synchronous I/O via the normal POSIX write function then. Okay, and that's that. So the last question is, of course, what will be next for Elbencho? That will be Elbencho 2.0, and in that I will be adding S3 object storage support, which is already done to a large degree. So coming soon. In that mode, you will just have the option to add some S3 endpoints and then specify a bucket like you would expect. And then again, the number of virtual directories that you want to create inside that bucket and some files / objects per virtual directory that you want to create in that bucket. Unfortunately, that requires a download of the Amazon SDK for S3, which is rather large, 1 GB. So it will probably not be enabled by default in the make command, but will be included automatically in the Docker downloads, or otherwise, if you build it yourself from source, then you can just enable it via the S3 support =1 make option. Thank you very much. And now happy benchmarking.